All right, well, welcome, welcome. It is fantastic to see all of you here tonight. Thank you for coming out and joining us. We have a fantastic program planned for you. What is left to discover our unknown universe? We're going to cover what we know about the universe, what we know about physics, how we know what we know, how we discovered it, and what we don't know, because there is so much that is left to discover, and we're going to get a preview of where we might be headed with that. To kick us off, it is my pleasure to introduce Daniel Whiteson. He's a particle physicist and professor at UC Irvine. His research pioneers advanced machine learning and statistical tools to analyze high-energy particle collisions. He also hosts a very neat popular science podcast called Daniel and Jorge Explain the Universe. I recommend it. And he's the author of 2 acclaimed popular science books, We Have No Idea and Frequently Asked Questions About the Universe. He's also the co-creator of a PBS television series about science for preschoolers and an all-around top-notch expert in explaining complex scientific ideas for a broad audience. Professor Whiteson, welcome.
Good evening, everybody. Thank you so much for enduring that feedback for a moment and for coming out here this evening. Thank you very much for the kind introduction. It's really an honor to be here tonight, especially with such an esteemed panel. And later on, we're going to hear from Fabiola. She's the director of CERN, basically the worldwide president of particle physics at the moment. And Hitoshi, who's just finished leading a study to direct the future of United States particle physics. So I feel a little bit like, a garage band who's been asked to open for the Rolling Stones and Madonna simultaneously. These guys really are rock stars. So very much looking forward to hearing what they have to say. All right, so let's get started. You guys are a smart audience. After all, you decided to spend your Tuesday evening hearing about particle physics. So you probably go to a lot of science lectures, and you're probably used to hearing scientists tell you about what they have discovered, what they have figured out, the incredible puzzles that they've unraveled about our cosmos. And that's wonderful, and we should all hear more of that. But tonight we're going to do something very different. Instead of thinking about the past and all the discoveries we have made, we're going to fast forward to the future and try to anticipate the discoveries that we might make. And the way to do that is to fast forward, do all the way to the forefront of human knowledge and stare into the abyss of our ignorance, so we can think about what's left to discover. All right, so as you heard, I'm a particle physicist, which means my day job is to try to unravel the secrets of the universe and figure out how it all works, which is wonderful and really a privilege, and I recommend it to everybody. But it's not actually what I wanted to do when I was growing up. And what I wanted to do growing up isn't even anything that was on this list of the most common choices, though I'm very grateful that scientist still outranks vlogger and social media influencer, for the moment. We'll see what happens when we get this updated. But what I wanted to do when I was a kid, I didn't want to be a scientist or anything here, was something very different. And before you ask, no, it wasn't professional basketball player, but thank you for asking. No, what I wanted to do was I wanted to be an explorer. I remember reading about the age of discovery. People could get on a ship and sail across an ocean and be the first person to set foot on Australia 70,000 years ago, or walk across the land bridge to America and walk down the coast. And you go to the Grand Canyon and it's amazing, but think about how the Grand Canyon was discovered. There was a first person to ever see the Grand Canyon. I wanted that thrill of discovery. I wanted to be the first person to know something or to go somewhere. To me, that was really, really exciting. And I was inspired by role models I saw as a kid. Calvin and Hobbes, for example, were always out there exploring and discovering treasures about the universe, in their trusty wagon, having crazy times. Here's an actual picture of me as a kid. I'm in the middle, in our wagon, as my brother's about to push us off into some crazy adventure. But I was excited about being an explorer when I was a kid, but as you learn more about it, you start to feel like, it's kind of history, right? Nobody's discovered a continent in quite a while. And there aren't any more islands for you to find and to name after your dog or whatever. It sort of feels like, maybe this is the kind of thing in the past. And thanks to satellite technology and Google Earth, there really aren't corners of the Earth left to discover. And think about the amazing progress that science has made. I mean, we have these incredible devices. You can get in an airplane and go across the world in a few hours. You have all of human knowledge and a lot of human idiocy and a tiny device that fits into your pocket. We've even made breakthroughs in like long-standing problems about snack foods. I mean, we solved the Cheeto burrito puzzle, people. I mean, you might be forgiven for thinking that we have most of the world figured out. You know, that everything is basically understood except for a few details that people are going to figure out. And this is how I felt as a kid. I felt like, wow, maybe I was born too late. You know, maybe the age of exploration is over. And, you know, it's just, I got to do something else with my life. Maybe professional basketball player is a better choice. Well, the message of my talk today, and what I want you to go home with tonight, is the idea that the exact opposite of that is true. I think we're actually at the beginning of a new era of exploration, a new age of discovery that's going to reveal crazy, bonkers things about the universe that Daniel, at 10 years old, couldn't even imagine. So what am I talking about? What is actually still left to discover? Well, the kind of things that I think are still to be revealed about the universe are the things I call big, fat questions. Questions which, if you knew their answers, would change fundamentally the way you felt about life. You know, it would change the way you feel about the context of our existence. It would change the way you lived your life on a daily basis. You know, big, fat questions. So if you walk down the street or you ask a random person, like, what's the most important question in life? Or what question would you want answered if you could have one question answered? You probably hear things like this, you know, what's the meaning of life? Or why are we here? Or what happens after we die? And these are great questions. I mean, if you knew for a fact exactly what happened after we die, it would change the way you lived your life, right? All right, but the problem with these questions, though they're wonderful, is that they're philosophy questions, which means, yes, they're fun to ask, and yes, they're fun to talk about, but you know, philosophy is not a discipline that's famous for finding answers. You know, one of the most widely cited papers in all of philosophy is this one, what is it like to be a bat? That they've been debating for decades, and spoiler alert, the answer is, we'll never know, right? So philosophy is wonderful, but the thing that's exciting to me is that there are other questions at the same level of importance, but these are science questions. Questions like, what is everything made out of? Or how did the universe begin? There is one true story about the beginning of the universe. And if you knew that, if you knew how the universe actually got its start, what was going on in the first few moments, that would change the context of your whole life. Just like discovering that the Earth is not the center of the cosmos changed our feeling about where we are in the universe and our place in it, right? And there's an answer to this question. And if we're smart enough and we work hard enough, one day people will know the answer to this question. And those people, looking back at us, they will wonder, what was it like to be so ignorant, right? To not know this very basic thing about your whole life, right? The way we think back on like prehistoric man and woman, looking up in the night sky, having no understanding of what they were seeing at all. The incredible information literally being beamed at them, totally misunderstood. They didn't know the context of their own existence. And I think actually we have more in common with those prehistoric ancestors than we do with our better informed descendants, because they will look at us and see us in the same way, totally clueless about big fat questions. So we can't dig into all of these questions tonight, but let's focus in on this one. What is the universe made out of? This is basically the question of my career as a physicist that I'm trying to understand. And I think it's a pretty basic question people want to know the answer to. I also think it's an ancient question. I think people have been asking this question since people have been asking questions, you know? I remember as a kid smashing rocks together, literally, and wondering like, how small a rock can you get? What happens if you keep smashing? Do they turn into something else, or is there a minimum rock size or something? Maybe it's not a surprise I became a particle physicist, but think about this kind of question. What is the universe made out of? And imagine you're a caveman or cavewoman physicist. You're the first person to ever think of this question. How do you tackle such a big question, right? How do you even approach it? Well, in physics, what we do is like, well, let's just try the dumbest thing first, see how that goes, and then, we'll figure it out later. So what's the most basic approach to answering the question of what's the universe made out of? You might start with a list. So say you're a caveman, cavewoman physicist, right? And you're like looking around you and like, okay, I'm in the universe, you're in the universe. What else do we have to explain if we're going to answer this question of what's the universe made out of? And you discover, okay, there's a lot of rocks in the universe, right? And lots of different kinds of rocks. And the more you look, the more you find this incredible variety of rocks that are out there that you need to explain, right? It's really mind-boggling, the sort of diversity. Once you confront the scale of this question, what's the universe made out of, you realize there's a lot to explain. You don't just have to explain rocks, you have to explain blueberries and ice cream and mushrooms and flowers and really weird strong guys to become governor of California. Like, it's a weird world out there, people. And if you're going to answer this question, you have to explain all of it. It's a dizzying, dizzying variety and complexity. And that's where the list idea breaks down. You can't really explain the universe, answer the question, what's the universe made out of, by giving a list, right? If you asked the oracle, what's the universe made out of, and it gave you a literal list of everything in the universe, you'd be like, that's cheating, come on. Right? I'm in one of those fables where you don't really get what you want, because it's not a satisfactory answer, right? The kind of answer you're looking for is not an exhaustive list, it's a simplification. It's a compactification to find patterns and to understand what's going on at a level deeper than what you can see. So how do you get there? You don't just list everything, you organize it. You look for patterns. You say, well, all these things are rock-like substances, and all these things you could eat, and these things have similarities, and you start to notice these things. And fast forward a few hundred years or a few thousand years past basically all of chemistry, and you can discover that something really incredible about our universe, which is that there's almost infinite variety, lavas and kitten and neutron stars and ice cream cones, all of that stuff is made out of basically 100 building blocks. Now, you might be thinking right now, hold on, I'm here to hear about CERN and particle physics. Why are we still talking about high school chemistry, right? This is basic stuff. It's basic stuff to us, but it's also, in my view, one of the most underrated intellectual achievements of all time. I mean, we have gone from infinite complexity to 100 things. That's a staggering simplification, right? On the path from infinity down to one object that explains everything, that's most of the way there. You have to ask yourself, like, why do we even live in this kind of universe where you can explain a huge number of different kinds of things using a few basic building blocks, right? It reminds me a little bit of, Legos, right? We live in a Lego universe where a few basic building blocks put together in lots of different complicated ways can make complex things. So complexity in our universe, the reason we have lava and ice cream and kittens and all these different kinds of things, doesn't come because the universe itself is complex. It's because of the arrangement of the stuff, right? Complexity comes from the arrangement. That says something really deep about who you are. I mean, you can imagine a different kind of universe, one where everything that's in it is made of its own thing. It's fundamental. Cats are fundamental. Hamsters are fundamental, right? Or cats are made of their own little cat particle, and that's why they're so weird. We could have lived in a universe where as you drill down, you don't find simplicity, you still find complexity. But we don't. So it's fascinating. Already we've learned a lot about our universe. But we don't just say, okay, we have 100 basic building blocks, we're done, right? That's a list. And lists have limitations. So what do? We look for patterns among that list. We notice there are lots of patterns, right? Some of these guys are shiny and conduct electricity. Some of these guys interact. Some of these guys don't interact. There are lots of patterns. That's what we call it, the periodic table, after all. And those patterns lead to questions. We wonder, why do these guys all have similar properties and those guys have different properties? And those questions we ask are the clues that lead us to another layer of understanding, to peel back a layer of reality and see what's underneath. And now, of course, we know that all of the structure of the periodic table comes from the structure of the atom itself, right? The electron orbitals are what determine how things interact and whether they're shiny or whether they're brittle or conduct electricity. All of that complexity comes from the structure underneath. So that's a really important lesson. That when you notice patterns that are unexplained, those are clues to lead you to understand a deeper level of reality. And we can go a little bit deeper. Inside the nucleus of the atom, of course, are neutrons and protons. Inside those are up quarks and down quarks. So put together up quarks and down quarks, you can make protons and neutrons, sprinkle around some electrons, and you have atoms. That means something kind of incredible. With just these three basic building blocks, electrons, up quarks, and down quarks, you can make anything. You ask a particle physicist to write a cookbook, for example, there's only 3 ingredients in every recipe, and they're actually, weirdly, almost the same ratios. What's the difference between a kilogram of lava and a kilogram of kitten? Well, they're basically the same ingredients, just put together differently. It's fascinating. The difference between you and lava is not actually that much. You're both very hot. So this seems like, okay, maybe we're almost there, right? Like, we've gone down from infinite complexity to 100, down to 3. Next year, we're going to figure it all out, right? Well, there's some wrinkles to the story, as always. It turns out these aren't the only 3 particles we found out there in the universe. The electron is an example of a lepton, and there's 6 of those. The up and the down quarks are examples of quarks, and there's 6 of those also. So here's a list of the particles. But again, the lesson is lists are not helpful, right? The way to understand the universe is to look for patterns, to organize these things and ask questions. So here we are at the forefront of human knowledge. This is as much as we know about the universe. We know the up quark and the down quark of the electron are there to make atoms and me and you and hamsters and ice cream and all that good stuff. There's also this other weird particle, the neutrino, we'll talk about in a minute. And there are definitely patterns in these particles because these first 4 are copied. The charm is a heavier version of the up. The strange is a heavier version of the down. And the pattern repeats again. The top is a heavier version of the charm. And as you move to the right, things get more mass. So just like with the periodic table of the elements, we were like, there's some strange patterns here. I wonder what those mean. Here we have strange patterns, which lead us to ask questions. Those questions, we hope, will reveal a deeper layer of understanding yet beneath this, but we don't know. You are now at the level of knowledge of cutting-edge particle physics, and we are standing here clueless, not understanding what these patterns are. But we can ask these questions. Questions like, why do we have all these particles anyway, right? Why does every particle have 2 copies? How many particles are there in the end? Why are some of them so massive and some of them not very massive? We don't know the answers to any of these basic questions, but we hope they'll lead us to some solutions. So let's walk through them. What are these particles there for anyway? So you need the up quark and the down quark to make me and you and your dinner, and basically anything any human has ever eaten or tripped over or thrown at their sister has been made of these 3 particles, okay? So why do we have the neutrino? Well, it's sort of an atomic-centric question to ask, right? We're made of atoms. Everything is made of atoms that we know and like, but the neutrino is still part of the universe. It's out there. In fact, neutrinos are everywhere in the universe. They're produced at the heart of the sun in incredibly copious numbers, and they come and hit the atmosphere, and we call them cosmic rays. So cosmic rays hit the atmosphere, and they're everywhere in our atmosphere. You don't even notice them. Trillions and trillions of neutrinos are passing through your body at this very second. Most of them ignore you. Occasionally, one of them bounces off your eyeball or something. You probably don't even notice. But neutrinos, we say, well, why do we have them? We don't know the answer, but we know they're there. They belong in the universe, just like atomic matter. And we hope that they're a clue, the pattern, the structure. They're helping us fill out this periodic table of fundamental particles so we can try to understand what's going on underneath. Another question is, why do we have all these other particles? Right? We have the up, the down, the electron, and the neutrino, and then we have them copied, and then copied again. That's really weird, right? That's a very obvious pattern. It's the kind of thing where in 100 years, physics undergraduates will be like, man, if I was around then, I totally would have understood it. It's so obvious, right? It's a screaming clue from the future, right? Maybe everything you need to know to win a Nobel Prize is right here on this slide. We just can't put it together yet. But we can ask some questions, like, why are there 3 versions? I think about like the fundamental theory of physics, if we ever get it. What numbers could appear in that theory? You write it down and, what if there's like a 7 in there? What does that mean? It means the universe is like 7-ish in some deep way, right? I mean, if you ask mathematicians, what numbers do you expect? They say 0, pi, 1, e. They don't say 3, right? The only people who say 3 are like the Catholics, and hey, maybe they're right. Maybe, the universe is fundamentally 3-ish. Who knows? So that's a deep mystery we don't have an understanding to. Another question is, how many particles are there? We've discovered these 12. That doesn't mean that there are all the particles that there are. It's just the ones we've found so far. We don't know if these particles are the tip of the iceberg, we don't know if these particles are all there are, or if they're the tip of the iceberg. There could be like millions of particles that the universe could produce. How could we possibly find them? Well, we don't know what these particles are, and you might think, how could you possibly discover a particle if you don't even know whether it exists and what it's like? Well, we can explore to discover new particles in sort of the same way that you can explore to discover alien life, right? You land on a new planet, you look around, you don't have to know in advance exactly the kind of alien you're looking for. You see something slimy and squiggling under a rock, you found it, right? Awesome. So in the same way, we can look for new particles using the quantum mechanical trick of a collider. A collider does something really awesome, which is that you take two particles, you smash them together, and what comes out is not a rearrangement of what went in. This is very different from your intuition about like chemistry, right? For example, you take hydrogen and oxygen, you click them together to make water, you still have the same original hydrogen and oxygen. It's still there, just rearranged, right? That's not what's happening here. Instead here, when you smash the particles together, the interaction happens between two particles that annihilate and turn into something completely different. This isn't chemistry, this is alchemy. We're transforming one kind of matter into another. And we can do it over and over again, and the amazing thing is, every time you do it, you can get a different answer. Because it's quantum mechanical, it's ruled by laws of physics, but each individual instance can be different. And that means something really awesome. If you smash particles together with enough energy, and you do it often enough, eventually you will reveal everything that can be made in those collisions. It's like getting a look at nature's secret menu of particles. As long as you have enough energy to spend, you can get anything on the menu, right? It's really amazing. So using colliders, we can discover particles we didn't know existed in advance, just by smashing particles together and seeing what comes out. Eventually, the universe will reveal everything that it can do with that energy. And one thing, of course, we have discovered recently, about 10 years ago, 12 years ago now, is the Higgs boson, famous boson, of course. And the Higgs boson is a ripple in a field that fills the whole universe. We call it the Higgs field. In sort of the same way that like the photon is a ripple in electromagnetic fields. And we're used to electromagnetic fields. They can do cool things like push and pull on electrons. The Higgs field can interact with particles, but it does it in a very different, very special way. It changes the way those ripples work in those other fields, so that it makes them harder to push and harder to slow down. So instead of pushing or pulling on them, it changes their inertia. Effectively, it gives them mass by changing the way those other fields ripple. Something we really don't understand about the Higgs boson, it's a big step forward to say, wow, now we understand how particles have mass. It's because they interact with the Higgs field. Yeah, but why do particles have different masses? Some particles interact with the Higgs field a lot. They get a lot of mass. Other particles fly mostly through, ignored by the Higgs field. They get very little mass. We do not understand why some particles have a lot and some particles have a little. So you might say, okay, we understand the question of why do particles get mass? Sure, but now we don't understand why they get different kinds of masses. We're like sort of kick the question down the road. So for example, W's and Z's, they get a huge amount of mass, but photons remain massless. It's a question about why particles get different amounts of mass. And if you look at the particles of matter, the up quark, the down quark, the electron, the neutrino, in the same generational structure that we talked about earlier, these are the masses of all these particles. And a unit particle physicists like to use mega electron volts. And to help you convert, here's the conversion between that and a chocolate chip, which is very easy. But the range, the thing you should take away from this is the enormous range of the masses of these particles. Some of them are very, very light. Some of them are incredibly heavy, like the top quark. This is something we just don't understand. And again, it feels like these are important clues. Somebody's going to look at this in the future and be like, oh, obviously this is because of X, Y, Z. Sometimes I feel like we are scientists in the far side, listening to dolphins talk to us and just not understanding the language they're using, so we're forced to just like write things down, like botanists, not even understanding what's going on. And if we only spoke the language, then it would all snap into place and make sense to us. One day maybe we'll have some moment of insight and realize these dolphins are just speaking Spanish to us. And so how do we do it? Well, we try to explore, right? We go out there and try to find new things about the universe. That means launching literal probes to alien moons. It means new technological eyeballs to look at the universe. And it also means smashing particles together at higher energies to explore the fundamental universe. But the questions of what's out there in the universe and what the universe is made out of are actually very, very linked. Because what we've been talking about so far, the particles that make up matter and me and you and kittens, is actually a tiny little fraction of what the universe itself is made out of. About 5% of what's out there in the universe can be explained in terms of atoms and these building blocks we've been talking about. So we've been spending thousands of years trying to understand matter, only to discover recently it's a tiny little bit of what's out there in the universe. A big chunk of this mystery pie is something we call dark matter. Dark matter is an idea that comes out of studying how galaxies spin. We look at galaxies spin and we wonder, why are the stars staying in the galaxy? I mean, if you put a bunch of ping pong balls on a merry-go-round and you spin it, what happens? Ping pong balls fly everywhere, right? So what's holding the stars in the galaxy? And people thought, oh, obviously gravity. So they went out and they measured how much gravity there is in those stars and asked, is it enough to hold the galaxy together? And the answer is not even close. These galaxies are spinning super duper fast. There's not enough gravity to hold them together. And yet they're not throwing their stars into intergalactic space. I mean, not usually. So people thought maybe there's a new kind of matter out there in these galaxies, something we can't see, something we didn't know was there, but it has gravity to hold these galaxies together. And what we call dark matter, it's a little bit confusing. You imagine something dark and black, but particle physicists think about dark matter in terms of how we can interact with it, how we could see it or touch it or push it or pull it. So here are the 4 ways that things can interact. You can interact via gravity or electromagnetism. This is the weak nuclear force and the strong nuclear force. And for dark matter, we know that it feels gravity because we invented it to explain this question of the missing gravity. We know it doesn't feel electromagnetism or the weak force or the strong force. We tried all of those things. And we tried a lot of things. I mean, we tried emailing it. We even looked it up on social media. It's just totally ghosting us. We cannot figure out what dark matter is. And it's not a small problem. I mean, in order to explain the spinning of galaxies and the structure of the universe, you don't just have to add like a little bit of dark matter. You have to take the existing matter and multiply it by 5 to explain the universe that we see out there. So whatever dark matter is, whatever dark matter is, it's the normal matter, right? We're the weird stuff in the universe. Dark matter is much more plentiful than what we see out there. And you know, this is a big idea to say, wow, the universe is chock filled with all this stuff you never saw before and nobody had ever discovered. It takes a while before people begin to believe this. And one way people began to accept this is to see other ways to observe dark matter. So dark matter can do something really cool, which is called gravitational lensing. It can bend space itself so that photons passing through that space change their direction. So you can imagine if there's a huge blob of dark matter between us and some distant galaxy, a photon leaving that galaxy in one direction or another direction, they could get bent both towards our telescopes, which means if you look up in the sky, you could see the same galaxy twice, right? That's gravitational lensing. You can tell that there's something big and invisible and gravitational between you and that galaxy. Another important piece of evidence for dark matter is that we recently saw a huge collision of clusters of galaxies. Like, we like to smash particles together. Astronomers like to smash galaxies together, right? They don't get to do it very often. They just have to wait for the universe to do it for them. So they smashed these 2 galaxy clusters together, and what they saw was really incredible. The dark matter passed right through itself because dark matter doesn't feel any of the forces that would cause you to smash into each other and create explosions. The gas and the dust did create those explosions, but the dark matter passed right through. It feels gravity, but that's not enough to prevent it from passing through itself. And we can see where that dark matter is because of the gravitational lensing of galaxies further beyond it. So this tells us something important, that dark matter is real, it's something, it's a kind of matter. It's a kind of matter, it has its own gravity. It's not just a misunderstanding of gravity for normal matter. We can separate it from normal matter. That doesn't tell us, though, what dark matter is, right? We know a lot about what it does. We don't know what it's made out of. We don't know if dark matter is made out of one kind of particle or 10 kinds of particles or really complicated arrangements of particles. We have a few theories about what dark matter might be, right? One is called the weakly interacting massive particle, or a WIMP. Another is the macho, massive astrophysical compact halo object. These are two real theories of dark matter because we just don't really know what dark matter is. We don't know what it can do. We don't know if there's dark matter physics out there and they're doing complicated things, dark matter chemistry even. There could be dark matter biology, right? Somewhere out there in the universe, there could be a dark matter physicist giving a dark matter lecture to a dark audience. Who knows, right? The questions are enormous about what dark matter is and what it can do. But even that piece of the universe only brings us to like a third of what the universe is made out of. If we're going to answer the question, what's the universe made out of, we got to address the 2/3 pie, right? This part of the universe is something we call dark energy, which is science code for we have no idea what this stuff is. And the only connection between dark matter and dark energy is the word dark. And to understand dark energy, you need to know a little bit about the history of the universe. So here's a very abridged history of the universe so far. Okay, so we had the Big Bang 14 billion years ago. Things spread out and cooled. Everything's moving away from each other. Then, finally, eventually, stuff happened, like cats were made and we had ice cream. So that's where we are today. And then people were wondering, what's the future hold? Is the universe going to turn around and crunch back together to great density? Is there enough gravity in the universe to pull it back together? Or is there not enough gravity in the universe and things are just going to drift out forever, cooling and getting further and further apart? These were the two big ideas about 25 years ago. And they went out to measure. They said, well, let's look at the history of the expansion and see if we can tell which of these is our future. And this is one of my favorite moments in science because the universe said no to option A, no to option B. It went for secret option C, which is like, actually, we're not slowing down at all. We're speeding up. So every year, this expansion of the universe is getting faster and faster. We call it dark energy, but that's just a description of our observation that the expansion of the universe is accelerating. It's not an understanding for how it's happening or why it's happening or what's doing it. We really just have no explanation for the cause of this expansion of the universe. Why is everything out there we see in the sky running away from us? But it does mean that the deep future very, very likely has other galaxies much, much further away. Things that we can now see in the night sky eventually will fall off the edge of the observable universe. So astronomers in 1 billion years or in 5 billion years will not be able to see the galaxies that we see today, right? So think about what has already fallen off the edge of the observable universe that we will never see. So we try to understand the universe, and we can make a pie chart of it. Most of it is stuff we don't even understand what it is. A big chunk is stuff we know it's there, we know it's matter, we don't know what it's made out of. And a little bit of the universe is stuff we have some understanding of, but a lot of open questions. And I feel like we're at this moment when we're studying this, when we're realizing, wow, we've been looking at a tiny little bit of the universe. We're like scientists who've been studying the tail of an elephant and only now discover, oh my gosh, there's more to it. Maybe we should walk around and meet the rest of it, right? There might be some answers there. There's so many questions about the universe that we don't have answers to. We haven't even had a chance to dig into tonight. Questions like, what is time anyway? This is a pretty basic question to want to understand about the universe. We know time and space are deeply connected by relativity, but we also know they're very different. Right? You can revisit a location in space as many times as you want, but you can't go back to the same moment in time as many times as you want. So space and time are quite different. There's lots of questions about space itself. How many dimensions are there of space, right? Are there additional spatial dimensions that are looped up that we can't see? We don't know the answer. What is space anyway? Isaac Newton told us it was a backdrop on which the universe actions played out, but we now know that's not true. Space can do really weird, interesting things. It can expand, it can bend, it can ripple, right? Space is much more complex. It's part of the universe, not just the backdrop. So we have lots of open questions about what the universe is made out of, lots of things left to discover, and I think that we are the beginning of an era where we might start to figure these things out. We're building as many colliders as we can and space telescopes and gravitational wave detectors. All of these things are going to get us to the promised future, that moment when maybe we understand the answers to these really basic questions about the universe. And those answers, I promise you, they're going to blow your mind, right? And it might be that in 200 years, people look back at this moment in history and they're like, wow, That was the time when they really started to figure it all out. Those were the exciting times in physics. I wish I had been a physicist back then. So thank you very much, and I hope you come away with that with the idea that we have a lot left to learn about the universe. Thank you. And if you're interested in these things, you can check out one of my books or my podcast, my TV show. And I just want to put a promo for, I have a new book coming out next year called Do Aliens Speak Physics? About whether when we meet aliens, we could actually talk to them about these secrets or whether they have their own ideas. All right, thanks very much, everybody. So I think we have time for a couple of questions, if there are any, before we get to the panel. Any burning questions about the nature of the universe? Theories of dark matter?
Daniel, what's your favorite of all these particles you talked about?
I think my favorite is the top quark. I got my PhD thesis on the top quark, and back then it was hard to make one. My PhD thesis was about 3 top quarks. And these days, of course, at CERN, we produce thousands and thousands and thousands an hour. So I feel like that grumpy old man, like back in my day, it took a year to make a top. You guys don't appreciate what you have.
In 30 seconds or less, can you explain how the multiverse works with all this?
The multiverse is a completely separate direction. It tries to answer the question, well, why is the universe this way and not some other way? It says, well, maybe there are other universes that are that other way. It's sort of an attempt to answer that question. But I hope that we don't need the multiverse, that when we get to the fundamental theory of physics, we realize, oh, it had to be this way. It could be no other way. That's my preference.
Thank you so much. Where does the Higgs boson fit into your particle framework?
Oh, great question. So the particles that I showed, these are the matter particles, the ones that make up stuff, that we call them fermions. There's a whole other set of particles I didn't show you, which are the particles that transmit forces. So the photon, the W, the Z, the gluon. There's a whole separate table. The Higgs boson fits into those. Yeah, but it's not a particle we consider like a matter particle. It doesn't make up stuff. Great question.
Okay, Daniel, we have a question here.
Are black holes made of dark matter?
Exactly. Are black holes made of dark matter? There's almost certainly some dark matter in black holes. The problem is that dark matter probably circles black holes without falling in very rapidly, because to fall into a black hole, you need to lose your speed. Like, dark matter probably orbits black holes the same way the moon orbits the Earth. The moon isn't falling into the Earth despite the Earth's gravity. In order to get the moon to fall into the Earth, you'd have to slow it down or bang into it, but dark matter can't do that. So probably it orbits black holes more than falls in, but I'm sure there's some dark matter in there. Great question.
And we got one over here.
Hi. Do we expect this theme of smashing particles together and finding smaller and smaller components to continue indefinitely, or do we have some lower bound?
Wow, love that question. Yeah, the answer, of course, is we have no idea. It's a pattern that's extended for a while. And so you might think the most natural answer is, yes, you should keep finding stuff forever. But it's pretty weird to imagine a universe that's infinitely regressive, right? Where nothing is made of itself, everything is made of something smaller. That's weird. It's also weird to think of a smallest thing, right? It'd be fascinating to discover it. We have no hints that the universe is one way or the other, except for very vague suggestions, like quantum mechanics says, that everything in the end is made of smaller stuff. And there are some scales to quantum mechanics that people can make very fuzzy answers and suggestions about how there might be a smallest thing, but we are far from really knowing anything concrete about it. It's the realm of banana peels and philosophy for sure, which I say in a positive way, absolutely in a positive way.
Is it possible for a particle collider to be the tool that produces a particle that is a dark matter particle? And if not, is there a different tool that we have that could possibly create dark matter particles?
Can we produce dark matter colliders? Gosh, I hope so, because I'm spending a lot of time trying to do that. Yes. We think if dark matter has some kind of interaction with normal matter, that when you smash protons together, eventually you will make dark matter. We are looking for it, absolutely. We haven't found any, but we're definitely looking for that. We hope so. Great question.
How did we figure out that dark matter wasn't interacting with a weak interaction or strong interaction when we don't know what it is?
Yeah. How do we know dark matter isn't interacting with weak or strong interactions? If it had strong interactions, then it would bounce off of us and it would cause all sorts of reactions. We would definitely see that because a strong interaction is very powerful. Weak interaction is very weak, so it would be hard to see, but we have huge tanks of liquid underground that are waiting for a dark matter particle to come and use the weak interaction to bounce off of one. And we know how many we would expect roughly, and we haven't seen them. And so we can rule out the weak interaction mostly. All right, well, thanks, everybody. We're happy to answer more questions later, but we definitely want to get to our esteemed panel. Thanks, everybody.